Wireless communication has advanced rapidly, and as we look beyond 5G, the next generation envisioned is 6G, a more intelligent system supporting diverse applications. At the heart of this shift is semantic communication, which focuses on transmitting the core meaning of information rather than just the raw bits. While current systems are built on bit-level transmission, 6G will leverage the essence of data to enable more intelligent and efficient communication. Early concepts in semantic communication often used analog signals, but these face significant compatibility challenges with today's digital hardware. To make semantic communication a practical reality, we must explore digitized systems that can integrate seamlessly with existing digital infrastructure. This evolution involves joint source channel coding, where deep neural networks achieve compact and robust semantic representations for high-performance tasks. We are moving away from traditional two-step coding strategies toward a new paradigm that treats semantic representations as the core channel symbols. A digitized semantic system bridges the gap between intelligent extraction and practical deployment by leveraging discrete representations. There are two primary paradigms for designing these digital systems: the probabilistic approach and the deterministic approach. The probabilistic approach employs stochastic modeling, where channel input symbols are generated by sampling from a distribution conditioned on the input data. In contrast, the deterministic paradigm constructs a direct mapping from continuous semantic features to discrete symbols using quantization. These methods are deeply rooted in neural representation learning, focusing on creating representations that are both informative and robust. The goal is to maximize the informativeness of these discrete representations while ensuring they can withstand the inevitable distortion from channel noise. Designing effective digital systems requires a focus on improving both semantic extraction and representation discretization to maintain robustness. This leads us to three key quantization strategies: scalar quantization, symbol quantization, and vector quantization, each serving distinct goals. Scalar quantization targets individual elements within encoded features, converting them into bit sequences for standard modulation. Symbol quantization remaps irregular constellation symbols into predefined spaces, aligning them with modern digital modulation schemes. Vector quantization focuses on designing a discrete codebook representing feature vectors by indices to significantly reduce transmission overhead. By sharing the codebook between the transmitter and receiver, we can achieve high-efficiency communication with minimal data transfer. Training these systems requires differentiable approximations, like the straight-through estimator, to handle the non-differentiable nature of quantization. The straight-through estimator allows gradients to pass directly from the decoder to the encoder, enabling smooth backpropagation. Soft-to-hard annealing uses a controllable relaxation to approximate quantization, balancing stability during training with final discrete performance. To achieve high efficiency, we propose a multi-stage strategy: pre-training in the analog domain before fine-tuning for digital systems. Analog pre-training allows the encoder to learn expressive semantic features from extensive datasets, establishing a robust foundation. The subsequent fine-tuning phase adapts these learned parameters to the rigid requirements and discrete constraints of digital modulation. Leveraging advanced architectures like transformers and Mamba is essential for capturing subtle semantic differences in information. Transformers excel at processing sequential data and capturing long-range dependencies across complex and diverse information streams. Mamba, a recently introduced architecture, offers even higher performance and inference speed compared to traditional sequential models. By utilizing these powerful architectures, we can capture subtle semantic nuances, resulting in more accurate and reliable transmission. We also incorporate principles like the information bottleneck to ensure that only the most relevant semantic information is transmitted. Maximal coding rate reduction further enhances performance by focusing the training on the most informative aspects of the data. Constellation design is another critical area, where we move beyond standard grids to more flexible and optimized patterns. Irregular constellations can better accommodate the non-uniform nature of semantic representations, enhancing overall system efficiency. Clustering techniques like k-means allow us to iteratively refine these constellations for better performance in noisy environments. Numerical simulations verify that these digital designs significantly outperform traditional systems across all signal-to-noise ratio regimes. Importantly, digitized semantic systems exhibit graceful degradation, maintaining quality even when channel conditions drop unexpectedly. This reliability makes digital semantic communication a key enabler for the high-demand applications of the 6G era. In multi-round transmission, digital systems offer superior resistance to distortion accumulation compared to their analog counterparts. Digitization also opens the door for traditional encryption, adding a much-needed layer of security against wireless attacks. It scales beautifully for generative transmission, achieving incredible detail even at extremely low bit rates for future networks. The next challenge is implementation on hardware platforms, requiring specialized hardware to optimize power and real-time latency. While challenges remain, the roadmap is clear, and collaborative research is pushing the boundaries of what's possible in 6G. Welcome to the next generation of connectivity. Welcome to the era of 6G.